Hi, I am Jainil and today I am here with my team to solve a problem. The problem being static solar panels. When a solar panel is just static throughout the day, it misses out on most of the energy that it can extract from the sun. The physics behind this is governed by Lambert's cosine law, which suggests that power collection drops off as the sun moves away from the normal of the solar panel. To solve this, we have set up a dual axis solar tracker.
Now, we will be moving on to the mechanical framework of this. This is the one which provides it the degrees of freedom, which are the two axes that it requires. While this structure is 3D printed for precision, the real engineering focus was the gimbal balance. The elevation axis was aligned precisely with the panel's center of mass. This mechanical sweet spot ensures the servos don't have to fight gravity to hold a position. By minimizing this holding torque, the system operates with high efficiency and avoids the jittery motion often found in unbalanced setups.
Now coming on to the electrical segment of our project, the electrical module acts as the system's sensory array. It uses 4 LDRs which change resistance based on light intensity. Since the Arduino can't read resistance directly, each LDR is built into a voltage divider circuit. This converts light into a variable voltage that our 10-bit ADC can finally process. We used 10K ohm resistors to keep the signal clean and responsive. To give the sensor's vision a 3D printed quadrant was added. This creates shadows that generate a voltage delta between the sensors, telling the system exactly which way to turn.
Now on to the firmware. This is where the raw voltages become intelligent movement. It uses a differential averaging algorithm to calculate error vectors. What is a differential averaging algorithm? It basically averages out the sensor values of all the sensors to give us error vectors. So if we can see here, this is averaging the value between the left top sensor and the right top sensor. This is averaging the value between the left down sensor and the right down sensor. This is averaging the value between the left top and the left down sensor. And this is averaging the value between the right top and the right down sensor. Now on to the motion. To keep the motion smooth, a tolerance threshold of 90 degrees was implemented. This acts as a digital dead zone, meaning if the light difference is too small, the motor stays still and they save power. The system then uses pulse width modulation to command the servos to the exact degrees required while enforcing software limits to prevent the wiring from tangling.
On to the few challenges we encountered during this project. The whole setup wasn't perfect immediately. During testing, the panel would sometimes overshoot its target and show increasingly erratic movements. Our team finally solved this by fine-tuning the 40 millisecond delay in the main loop, which effectively matched our code speed to the physical movement of the tracker.
I would like to conclude this now. In the end, we created a system that doesn't just wait for the sun, it actively pursues it. It's a small-scale demonstration of how simple sensors and smart logic can make a renewable energy much more viable.